Okay, excellent. So I'm going to change the pace here and talk about something that you've probably not heard much about, except for people that did the practicals with Jeff and I yesterday. Can I ask, before I start, how many people do materials synthesis in their home lab? Oh, good. Okay, good. So what I want you guys to do is to interrupt me as I go if you have questions. And part of the reason I want you to interrupt me is I'm not totally sure this will take 45 minutes unless you do, okay? So please interrupt. Okay, so what I'm going to tell you about are some of the things that we do here with respect to synthesis of inorganic crystalline materials and our sample preparation techniques. So I think before I proceed, of course, I should say that there's an even larger universe of types of materials that you could grow, like polymers and, I don't know, fancy devices and things like that. That's not really my specialty, but if you were interested in those sorts of things, I might be able to point you in the right direction. Okay, so these are the folks here who are spending a lot of time with materials preparation. I just want to flash their faces up here so that you might recognize them in the hallways. Our crystal growth guru is Theo Siegrist. He had a long career at Bell Labs, and in fact, he knows everything about crystal growth, and of all different types, okay? So if you have a question that I can't answer, I'm sure that Theo can answer it. You have to be ready for some long stories, though, okay? Okay, so then Luis Balikas is a relative newcomer to crystal growth, but his group does all sorts of vapor transport and molten metal flux growth, which I'll tell you more about. Jeff Whalen was a student of Theo and is now a research faculty here. He's also built up his own crystal growth business. He's an entrepreneur, so if you're interested in that type of career track, I think my experience has been that academics know nothing about that, so you could talk to someone like him. He's a pretty good resource. Tiglit Basara is a postdoc working with Theo. Both of these guys are also what you would call card-carrying crystallographers, which is pretty unusual in the physics community, and I'll return to that later. Christiana Beekman is a physics faculty who specializes in thin film growth. So she's the go-to person for that, and then me. And I'll tell you, actually this talk is really biased towards what I do, so you'll see a lot of that. Okay, I've got my clicker. Okay, so I want to tell you that actually we're very interested in collaborating. So if there is a material that you're interested in having that you can't get at your home institution, you can always feel free to contact us, and there's a good chance that we can grow what you want. We have people here that specialize in oxides. We have people that specialize in intermetallics, thin films, and so on. So I think we have a lot of capacity to help you out if you can't get something at your home institution. Okay, and this is really important. I mean, I think that you guys already know this, but I want to emphasize it. You should think of the periodic table as your playground, okay? It's not a static entity that's just done, right? In fact, if you think about all the different types of combinations that you could potentially make, you know, even in stoichiometric forms, I believe that we've really only started to scratch the surface of all possible combinations. And then if you take into account the fact that really interesting behavior frequently occurs in chemically substituted systems, you know, we're novices, you know, even though researchers have been working on solid state chemistry and physics for, I don't know, 100 years, 200 years, we really know almost nothing about this. So it's a wide open field, and anyone can get into it, okay? All right, so just to illustrate some of this, I think part of the story is told by the search for superconductors. And you guys have all seen this plot, right? This is something you're totally familiar with. And it's just a plot of superconducting transition temperature versus year with some important events along the way. And all that I want to tell you is that, you know, starting with the discovery of superconductivity back in what was it, 1911, I guess. Well, people worked hard, developed new types of conventional superconductors. TC went up. That was great. But around about 1980, there was a huge explosion of new discoveries, right? Starting with the heavy fermion superconductors, which were the first truly unconventional superconductors, where phonons weren't responsible for the superconducting pairing mechanism. And that was a complete surprise at the time. I mean, these days we take it for granted, but at the time it was a totally wild and bizarre result. And most people didn't believe it. But it wasn't so long after that that the cuprates were discovered, which are kind of having a new renaissance right now. And then, of course, the work that's been done on the iron pnictides recently, and then even this amazing result in hydrogen-sulfur under really high pressures, where you can get a superconducting transition up around 200 Kelvin. So, you know, just imagine, this is what has been done with our limited resources in the past 100 years. You know, it's a wide open field. I think this is really exciting. And superconductivity is not the only thing we care about. You know, this is just one really obvious phenomena that you can find in condensed matter. And it's driven by materials. Okay. Another way of looking at this, and here I particularly want to emphasize that it's important to look beyond the pure stoichiometric compounds, right? Most of the most interesting behaviors that we find are actually in tuned materials. And tuning can be accomplished using something like applied pressure or high magnetic fields, right? Or chemical substitution. And in fact, you know, what we've learned about superconductors, at least, unconventional superconductors, is that there's a type of universal phase diagram where you may suppress some ordered state with a tuning parameter, like chemical substitution. When you suppress it, you might get something called a quantum critical point that we could talk all day about, but okay, that's a place where a second order phase transition is pushed to zero temperature that may be protected by a dome of superconductivity with above it a region of breakdown of Fermi liquid behavior, and then eventually a recovery of a Fermi liquid behavior. And in fact, now there's more than 50 different families of materials that can sort of be crammed into this paradigm, okay? It doesn't mean that there's necessarily one picture to understand the physics of these things, but it's fairly compelling that you can start with something that you might say, oh, that's not very interesting, it's just some, you know, lame antiferromagnet, but you start tuning it, and pretty soon you have a breakdown of one of the great pillars of modern condensed matter physics, the Fermi liquid, and you have this amazing unexpected superconductivity. So I'm trying to tell you, tuning things is good, and chemical substitution is a good way to do it. But of course, in order to be able to do that, you've got to have some capacity for material synthesis. And so I'll switch gears now away from the science and physics and just tell you more about what resources are available here, tell you about some of the techniques. And this is where you should interrupt me, because crystal growth people, just like everyone else, are always using jargony terms. And if you don't know what I'm saying, tell me. Yesterday there was a question, for instance, about what is annealing, and I can define terms. It's no problem. Okay, so what we specialize in here is synthesis of inorganic crystalline materials. And what this means is that we span materials going all the way from some sorts of transparent insulators to, I think this is a semiconductor. This comes from Segrist Group. Okay, some ruby, that's kind of neat. Heavy fermion metals, like these guys, and topological or Dirac-Weil materials. So I think that within the families of crystalline materials, you can ask for almost anything, and we can probably come up with it. So I want to tell you, like I said, what resources are available here. I want to go into some detail about what crystal growth techniques are commonly used by our groups, and then to tell you about our crystal growth facility and what you guys could potentially have access to. Okay, so here's an overview. This is sort of generally what you need for crystal growth. So, of course, you have to make it out of something. So we have chemical stockpiles We're really lucky. Theo Segrist brought a huge amount of chemicals with him from Bell Labs when he moved here, when they shut down. I don't know how he convinced them to let him take all that stuff, but he did. So we have a lot of materials that are available to use. Okay, benchtop equipment, including scales and sort of typical things like that. We have lots of furnaces. These are just some of them. These are my favorite furnaces, but Theo likes little tiny ones, so okay, fine, doesn't matter. They're just a way to get to high temperatures. We have a quartz bench. How many people are familiar with what a quartz bench looks like? Okay, so I think, well, you'll definitely see it in the practicals, and half of you have already seen it. It's basically an apparatus where you have a plumbing system. You have a very hot torch. Actually, it's right here. This is a hydrogen-oxygen torch. And the flame that comes out of this is hot enough to melt quartz. That's really hot. But it's an extremely useful tool because what it lets us do is to enclose materials, like our starting materials, after we weigh them out, lets us enclose them in a quartz tube under argon or under vacuum so that we can do reactions in clean environments. So this is an extremely useful tool, and we can help you out with it anytime. We have more advanced apparatuses, which I'll return to for crystal pulling. And then another really wonderful thing that we have, and a lot of institutions have, are facilities for handling air-sensitive samples and their storage in an argon glove box. And I think you've probably all noticed that as you go down to the user cells, there's an argon glove box down there that's available for you to use. I think Tim's in charge of it. Okay. So now let me tell you about some of the crystal growth techniques that we use. So the most rudimentary thing that you can do is something that Jeff likes to call shake and bake. Other people will call it solid state reaction, but he's the cool guy. So, okay, so shake and bake. What is it? This is a way to make polycrystalline materials. And let me take an example. If you wanted to make YBCO, for instance, you could start with yttrium oxide, barium oxide, and copper oxide, just some powders of this stuff. And you could grind it up in a mortar and pestle and then press a pellet of it using a press like this. We have all sorts of different presses, and Jeff will give his whole spiel on presses later. So once you press a pellet, actually it'll look something like this. This is the finished product, but pellet will look something like this. And since we're talking about an oxide in this case, you can just take that thing, put it in a furnace, and react it. When you do this technique, the idea is to not go above the melting temperature of the material and to just drive a reaction between the grains. So that's why it's called solid state reaction. You might also call this annealing, although that's kind of a little bit of a fuzzy term. Okay, so on the other hand, if you wanted to do this reaction in an inert gas environment, you could just go ahead and seal something like this up in quartz tubes and then carry out the reaction. So this is a straightforward way to make large quantities of polycrystalline materials. There's all sorts of details you can get into, particularly with respect to how fine are your grains and how hard do you press it and what temperature should you react it at, and so on and so forth. And that's kind of the art of growing these things. But in a nutshell, this is solid state reaction. I should mention that what is normally happening with solid state reaction is that you typically have to fire and regrind many times to get a uniform sample because you're just relying on the reaction at the grain boundaries. And so it can be very inhomogeneous to begin with. So this can be a lengthy process, but it's a good place to start. Okay. So another way to produce polycrystalline materials is using arc melting. So this is also very straightforward. And the idea here, well, first of all, this is used for producing polycrystalline intermetallics. So where the shake and bake might be good for oxides that you couldn't melt with an electrical arc, this is good for metals where you can drive a current through them and actually put them into the liquid state. Okay? So the idea here is that you might take your precursors and load it into this sample hearth. And then I don't show it here, but actually you bring a bell jar onto this, right? And then you can pump this thing out, and you can get a pretty good vacuum on it. If you want to have a fairly clean atmosphere, what you'll do is to refill it with argon, and then pump it and refill with argon and pump it, and so on and so forth. And sooner or later, you have a pretty clean environment in there. Then you'll refill with argon, and what you can do, so this is just a extended welding tip from a power supply. And what we do is that we just drive basically lightning, through the sample. And if you do that, you can melt almost anything if electrons will flow in it. So it's pretty fantastic. I mean, you guys should see this sometime. Okay, so if you put the lightning through here, you can get up to something like 4,000 degrees C. So it means you can even melt refractory materials. So as an example, when you put carbon into things, usually the melting temperature goes very high. Or if you put boron into things, the melting temperature goes very high. But in this way, you can actually react things that include boron or carbon or other refractory metals like tantalum and niobium and so on. Okay, so here's an example of what will come out. Actually, this is a boron-containing material. So it's cerium, ruthenium-2, gallium-2 boron. Each of these elements actually have a pretty high melting temperature, except for gallium. Okay, and the way that you would make something like this is that you'd have a little bit of a strategy. You'd put the cerium and boron next to each other, because if you look at their binary phase diagram, how many people are familiar with binary phase diagrams? Okay, so one of the neat things about materials is that in chemistry, when you mix two materials together, it may turn out that the combinations of them could have lower or higher melting temperatures than the individual pieces. All right, so and the place where those melting curves come down, if they do come down, is called a eutectic. Okay, so for instance, for cerium and boron, boron's a giant pain. I mean, if you just put boron in there and try to melt it, you're probably not going to succeed. But if you combine cerium and boron, actually the melting temperature falls down pretty far. So what you can do if you want to grow something like this is to first, put the cerium and boron next to each other, and then melt the cerium from the side and let the boron sort of bleed into it. And that's a good way to handle materials like that. And then you just come along and combine it with ruthenium and gallium. And you can see that it actually produces a really beautiful crystal. And here, you can even see that there are facets. So even though you heated this thing to 4,000 degrees C, and then you let it cool at an unbelievably fast rate. Okay, I mean, this thing is sitting on a water-cooled hearth, so it goes from 4,000 C to about 800 C in a fraction of a second. So even though it cooled that fast, it still forms grains. And in fact, in a material like this, you can even break it and extract a single grain that might be a single crystal. So actually, Russian researchers love to do this for some reason. That's been my experience. Okay, so maybe I've dwelled on this for too long, but I really love this technique. The other thing that I want to tell you is that sometimes you may want to perform your reaction in a refractory metal crucible, like tantalum. And one of the best ways to seal your material inside of such a crucible is using an arc furnace like this. So all that these are reactions where we've made uranium ruthenium-2 silicon-2. We've stuffed the material in there, we've pinched the ends, and we've just arc melted the end. And when you do that, you can go to high temperatures as long as you keep this under an argon atmosphere, so it doesn't oxidize. You can put things in here that have really high vapor pressure, so without blowing them up. In a quartz tube, you have to be careful to avoid blowing things up. Okay, all right. So that's one technique that we use a lot. Questions? Yeah.
When you do arc melting process, it's rapidly cooling at the same time. So when I try to grow or melt, let's say at really high vapor pressure, something like that,
Yeah.
that really messes it
That's
up.
really hard. So I should have said that. Arc melting is not well suited to high vapor pressure materials.
So what happens to follow?
What I would do, okay, so are we talking about like phosphorus or
Similar to
arsenic or something like that? One thing that you can do, okay, there's a few routes. One thing you can do is this. If you can get your material sealed inside of here and then heat this up to a very high temperature, it's no problem. I mean, this can hold a lot of pressure. A different way to go about doing it is to look at the binary phase diagram for the high vapor pressure element and the other elements that you want to put into your material. So for instance, with the iron arsenides, there's a trick. And that is that iron, has a low vapor pressure. Arsenic has a high vapor pressure. But actually, they have a nice deep eutectic where the melting temperature of iron arsenic 1,1 is pretty low. So what you can do is you can seal iron and arsenic chunks in a thick-walled quartz tube. It's better to use thick wall. And then sort of spread the material out so it doesn't have the reaction all at once. And then slowly heat up to that temperature where the reaction can start to happen. And what will happen is the arsenic will sort of vapor transport itself and start to react with the iron. And if you go slowly enough, it gives enough opportunity for it to turn into iron arsenic. And then the vapor pressure of the iron arsenic, in fact, is very low. So that's you have to look at the vapor pressure curve and the binary phase diagram. Yeah. Oh, well, it could be as big as my thumb. Yeah. You could. So the thing you're going to encounter if you try to put an alumina crucible in one of these is that it's possible. You can buy that size tantalum, but it's expensive. Yeah. So, but what you should do before you even think about using an alumina crucible is just look at the binary phase diagram of tantalum and the other stuff. And if there's no phases forming below your growth temperature, then you don't even have to worry. Tantalum is very non-reactive with a lot of things. It reacts with some things, but a lot of times you can get away with a lot. I've not been able to. The tantalum ages. And when you first get it, it's very malleable. After a firing, it's very brittle. Yeah.
I have a question on solid state reactions.
Sure.
When you make your powder,
Yeah.
then you do some ball milling,
Yeah.
high energy ball milling, so you break it down by material, right?
Yeah.
But while you're making it, it's build the grains.
Yeah.
How does it? I mean, on one side you're just destroying it, and then you back it again. So what is happening here?
Well, yeah. I mean, there's several steps there. So, like you said, when you're ball milling it, you're breaking it down into smaller and smaller grains, right? When you press it, you're putting those grains in close contact with each other.
Okay, no,
It-
it's in unpressed.
Oh, unpressed.
Just taking the powder.
I see.
Ball mill, and then again, just the powder.
I don't know if that would be so helpful to be to be honest, because when you grind and press, the idea, at least what I'm thinking of when I do that, is to reduce the amount of inhomogeneity. And the only way that I think you can do that is by, let's say that you have a piece of material that's 90% one thing and 10% something else, but that 10% is kind of, I don't know, just distributed all around. So when you ball mill it, you sort of break up those pieces and distribute them more finely. And what you're hoping for is that they're going to encounter the other non-reacted stuff, right? So let's say you started with YBCO, and you started with yttrium oxide, barium oxide, and copper oxide. And you reacted it, you had 90% YBCO, and you still had 10% yttrium oxide, barium oxide, copper oxide. So you just want to put those things, as much as you can in contact with each other and drive their reaction again, and then do it again and do it again. I think if you ball mill something and then just have the powder sort of spread out and react that there's going to be a lot less opportunity for those non-reacted pieces to encounter each other.
Okay, and one more question on that. So when you center the whole thing at a high temperature,
Yeah.
and you break it down by ball mill,
Yeah.
when you press it again, would you have more porosity in there?
More porosity. I don't know. I think it might depend on how your precursors behave. But my experience has been that as you react it more and more, that it becomes more and more tight packed, because it's, you know, like same stuff packing in with same stuff.
It's hard for formulae to make it, to break it down to small.
It can become hard, yeah. But a lot of these things actually are kind of, if you had a single crystal of it, are pretty brittle. Well, not always, but they can be very brittle. So it means that you can break it down into very small particles. It would be material specific, I think. I think if you tried to ball mill some iron arsenic stuff, it would be a different story. It's more malleable. Yeah.
How you fill the materials with a half-wafer barrier?
It's tricky. So it takes some experience. What we do, and I'll just tell you, what we do is we start off with the tantalum tube. So imagine you just have the tantalum tube. We cut out a section of it like this, and then we press the end of it. And I like to have a fairly significant length of pressed. So this here is probably about half of what I started with, right? So I pressed and hard pressed a good long length of it. And then what I do is that I fold up kind of a dovetail on the end. So it's flat to start with, and then I fold it up like this. And that's important because tantalum doesn't like to wet to itself. So if it's flat, it'll sort of ball up away. But if it's dovetailed like this, the melt will fall down. And then you just bring the arc, and in no more than a second, you just bring it across the end. And if that didn't seal it, you wait a minute or two, let everything cool down again, and then you bring it across the end again. So it's possible to do, but it's challenging. Yeah, we've done it with phosphorus before, for instance, and we can do it with gallium and tin and all sorts of low melting temperature things. Yeah, you have to have an advisor that's willing to let you waste some tantalum in learning how to do it. Yeah. Okay. Okay. Further questions?
So when you do this kind of arc melting process, oftentimes as it happens, like if you want to do really homogeneous reaction, you want to flip the button and remelt it.
That's right.
And
Yeah.
sometimes if you have a low thermal conductor, it just explodes.
Yes.
Lose your mass.
Yes.
And go over and start over.
Yeah.
That's what I don't want to do. So
Yeah.
how do you decide all those kind of stuff? Like when you stop, okay.
Yeah. So it's on a case-by-case basis. If I am arc melting something and I discover, so usually they don't explode. If it's going to explode, they don't explode on the first melt, right? But they may explode on the second or third melt. If I flip it and it explodes, then I say to myself, I'm never flipping this one again, right? I just start over and I do it one time and then maybe anneal it, to try and make it a higher quality. Yeah. But a lot of these materials, even after one flip, if it's a line compound that will form directly out of a melt, you can have a homogeneous mixture after one melt. Maybe you should sit on it with the arc, for twice as long as you normally would, or something like that. Yeah. Oh, I'll get to that. Yeah. I'll get to that. Okay. Yeah, I'll come back to that. Okay. I'm going to go on. Okay. So those are the two main ways that we typically use to make polycrystalline materials. But okay, if you're making measurements in high magnetic fields or any magnetic fields, you might like to have a single crystal, right? Because you'd like to put the magnetic field along a certain axis. Behavior can be different if it's magnetically anisotropic or things like this. So we like to have nice big single crystals. And a really rudimentary way of doing this is to take your polycrystal material and do something called the Bridgman technique. And what this is an apparatus that we have here that one of Segrist's students has been working on. And all that it is a tube furnace and a crystal puller. And so what we'll do is to fill an ampoule or a crucible or some embodiment, which is what Jeff likes to call these things, and hang it off the end of this, and then we'll drag it through the hot zone. And if the thing that your polycrystal is sitting in has a nice shape on the inside, like it comes down to a point, then it can happen that if you drag this through in the right way, let's say you go down, that you want to get close to the melting temperature or just above the melting temperature, okay? And as you drag it down, that material down at the point will melt, and then as it comes out of the hot zone, it'll solidify again. And that'll bias the grain. It may form more than one grain, but okay, you hope it makes one grain. And then you slowly draw it down, and then as the other liquid zone, passes through the hot zone, then it's going to nucleate off of that single grain. And if it's a material that likes to, it's a line compound, first of all, and it likes to form grains, you may be able to get single crystal grains to propagate up and out as you pull it down. Another thing that's worth knowing is that even if you start with more than one grain, there's a tendency, if things are uniform inside of your crucible, that one grain will eventually win out over the other grain. So if you have a long ampoule filled with polycrystal and you're willing to wait that long, you might be able to get something that starts off as 2 grains to eventually transform itself into 1 grain at the higher point of your ampoule. Yeah? Well, it depends. So you could do it in atmosphere, I guess, if you had the right material. I think it's more common to seal your material, for instance, in a quartz tube. You can buy crucibles, for instance, that come to a point. So you could put an alumina crucible inside of a sealed quartz tube. And if you're good, then maybe you can even make a little loop of quartz at the top so that you can put a hook in there. But there's other ways to hold the ampoule if you can't do that. You can't see it. So this is a very tricky technique from that point of view. Like you have to know what is the melting temperature, which you can find out other ways. And then you have to carefully characterize your furnace so that you know that the furnace is actually getting to that temperature. And then you just have to set it up and go. Maybe. Well, first advantage is that this is cheap, okay? They've been doing this since the 1940s or 30s, probably. I would also say, so I'll come to the image furnace in a few slides. I would also say that the image furnace is particularly well suited for insulators. This might be more flexible. Doing intermetallics in an image furnace is really quite challenging. So, okay, other questions? Okay. So now flux growth. I want to tell you about flux growth because this is my favorite thing. So what is molten metal flux growth? It's a technique to produce single crystals. It can be used for intermetallics and oxides. And the idea here is just that you use some material. So here I've shown you sort of just a chunk of indium. So you use some material that has a low melting temperature into which you can dissolve other materials with higher melting temperatures. So for instance, this is coming back to the binary phase diagrams. You can always determine whether or not you'll be able to dissolve element A into element B just by looking at these things. So for instance, if I wanted to make cerium cobalt indium 5, which is a famous heavy fermion superconductor, it's really straightforward because indium is a nice flux and cerium and cobalt easily dissolve into it. So what I'll do is I'll take a whole bunch of indium, maybe at a ratio of 10 to 1, indium to cerium, indium to cobalt, and I'll put the cerium and cobalt maybe down on the bottom of the crucible, and I'll pile up the indium on top. What you do then, and I should say too that you want to think about what type of crucible you're using, and even if you really need a crucible. So some fluxes that you might use don't have any bad effect on quartz, and I can help you to know the details of that. So for instance, zinc doesn't care at all about quartz. Or quartz doesn't care at all about zinc, so it's totally safe. But indium, I think it's better to put it in an alumina crucible. Okay, so in any case, you seal this material inside of the crucible under vacuum, okay? And then just take these things and put them inside of one of these giant resistive furnaces. And you can't see the crucibles here because they're sitting inside of large alumina crucibles that I just use to hold them, to keep them from falling down. You can then take the material through some heating curve, which is typically something like, heating up at 50 or 100 C per hour, dwelling at some temperature, maybe 1200 C. I think I wrote that because it's an advice to not go above 1200 C if you're using quartz ampoules. They start to get soft, and I think they melt by 1300. Okay, so be careful for 1200. And then you cool down at some ramp rate, I don't know, 5C, 1C, whatever you like. And if you've done it, if you've done what the crystal's like, and it's different for every material, you can form very large, sometimes very large, single crystal specimens. And these are sort of, I don't know, in a way as big as they get, okay? So do you have any questions about this technique? Because it's easily implemented pretty much anywhere, and it's a very useful tool for making big crystals. Renee's looking like I'm almost out of time. Okay, if not, I'll keep rolling, and I'll probably only get to the end of the crystal growth techniques, and Jeff in the practical covers a lot of the characterization techniques that I wouldn't talk about anyways. Okay, so we talked about that, this is another example that basically amounts to to flux growth, but it's a low temperature technique where you can use water-soluble starting materials and use a reactor of some sort. This is generally useful for making some sorts of ionic crystals or insulating sorts of things. It's pretty interesting. Jeff can tell you all about this because his business does this. Okay, floating zone image furnace. This is a technique that's really pretty sophisticated, and it takes some practice to get it right. The idea here is that you may make a polycrystalline rod of some material. Actually, this is a piece of ruby before it's turned into a single crystal. You can do this using shake and bake. You just have to use a special shaped die when you press your material. This is a technique for converting polycrystal into single crystal material. Okay? The way this is accomplished is by placing your polycrystal stuff on a pull rod in between two mirrors that actually just have really strong light bulbs in them. You close these two mirrors down and focus the light onto a point here that allows you to go up to temperatures near 2200 C. In these two-zone or two-lamp furnaces, that's kind of the upper limit. There's other systems now that will take you to higher temperatures, but our systems only go this high. And when you do this, if you have a material that's a line compound and will form directly out of the melt, you can convert your polycrystal into single crystal. And again, you typically start off with several grains, but if you pull the crystal for long enough, that'll convert into a single grain. All of this is done inside of a quartz tube enclosure where you can flow specialty gases or whatever you like. And so it's really pretty powerful. I mentioned that this is mainly used for growth of oxides because controlling this environment is a little bit challenging. So if you wanted to grow intermetallics in there, in order to avoid oxidizing them at high temperatures, you'd have to make a pretty nice gas flow circuit. We've tried to do that here with our systems, and it's been a real challenge. So I wouldn't advise trying to grow intermetallics in a system like this. But, and I'm just kind of going fast, we can talk more later, but if you want to grow large single crystals of intermetallics, you can use something called the Czochralski crystal growth technique. Okay? And we're actually building such a system here right now. Typically, these systems are very expensive and large, and not many places have them. But the idea is that if you can heat your metal, which is in this hot zone here, and it's actually this bit down here, if you can heat that above the melting temperature, and you might do that using an arc furnace setup, or in our case, we're using an RF furnace setup. If you can do that, and then insert a pulling finger that's made out of a material with a very high melting temperature, it's then possible to pull a single crystal out of that melt. And again, this relies on the material that you're trying to grow being a line compound. That's very important for this technique. Okay, so if you talk to me in 6 months, I might be able to help you grow single crystals this way. We're not quite there yet. Okay, one last crystal. Okay, I'm going to stop on this next slide after this one. Okay, and then we can talk informally about how to characterize them with X-ray diffraction. Okay, last technique that I want to tell you about that is really powerful is chemical vapor transport. The idea here is that you may make a polycrystalline precursor of some material. So for instance, we've recently been working on a Dirac metal, zirconium-2, tellurium-2 phosphorus. And actually note that these are high vapor pressure elements. So this is one way to deal with your high vapor pressure elements. So you'll make a polycrystalline precursor of this, and I can promise you that the polycrystal did not look like this. It looked awful. And then you can take some iodine, or there's other vapor transport agents. But what makes a good vapor transport agent is that it should have a high vapor pressure, because the idea, and it should be kind of reactive with the stuff that's in there. The idea is that you seal your precursor in a quartz tube, maybe a long one, with iodine as a transporting agent, and then you place that in a tube furnace. And you can even be really rudimentary about it, like we are. I'm not even talking about a 2-zone tube furnace, just a tube furnace. It naturally has a temperature gradient. And so what you do is you hang part of the tube out into the cold zone, and you have a hot zone. And what this does is it drives convection inside of the tube. And if the material is, if you have the right growth temperature and the material is, acceptable for forming, you can convert, really terrible looking polycrystalline material into enormous single crystals of this sort. And in fact, in this growth, the size of the crystal was only limited by the diameter of the tube. So really a fantastic technique. And my impression is that it's underutilized. Okay, so let me give you one last slide. If you can't get what you want, okay, if we can't help you, if no one at your home institution can help you, there's another resource that I think is underutilized. And that is that when Bell Labs was operating, this guy in particular, Joe Ramika, was extremely active in crystal growth. And so what that meant is that they had a huge library of crystalline materials that they saved. And in fact, when Bell Labs closed, Professor Art Ramirez, who's at UC Santa Cruz, got to take the entire library. So he has a huge library of crystals that he wants to share with the world, okay? So you can go to his website and you can browse what he has. And it's pretty well cataloged. And you can find almost anything. Well, I don't know about almost anything. You can find a lot of things there. So I really encourage you to go and look at that resource and see how it works for you. Okay, so I made it through crystal growth, and I'm going to stop here. Thanks.